Hi to all. Today I am going to start one more chapter, that is electromagnetic induction. In this, first of all, what is electromagnetic induction and what we are going to discuss in this chapter. Electromagnetic induction means, previously in the moving charges and magnetism chapter, we discussed about one thing, that whenever current passes through a wire, around that current carrying wire, magnetic field will be produced. If compass placed near the current carrying wire, it will deflect. That means current carrying wire, around the current carrying wire, magnetic field will be produced. That means current carrying wire can produce the magnetic field. Then that means like that electricity is linked with the magnetic field. We can generate the magnetic field from the current, but is it possible to generate from electricity from the magnetic property? Right? Then practically the Faraday and Henry scientists observed that we can generate the current by change in the magnetic field. Then that phenomena is called as electromagnetic induction. Induction means producing. Electro means electricity. We are producing the electricity by change in the magnetic field. Now let us see what is electromagnetic induction. Electromagnetic induction is the phenomenon of, the definition is the phenomenon of generation or the production, the phenomenon of generation of current or EMF in a coil due to change in magnetic flux link with it. Magnetic flux link with it is called as electromagnetic induction. This is electromagnetic induction. Electromagnetic induction. Okay, the phenomenon of generation of current or EMF in a coil due to change in magnetic flux link with it is called as electromagnetic induction. What is this in this? Generation of current or EMF. EMF means electromotive force. Okay, in a coil, when current or EMF generates in a coil, that generates due to change in magnetic flux link with it is. If you change the magnetic flux, then current will be produced. This is called as electromagnetic induction. Now, to know this electromagnetic induction, just Faraday and Henry, these two scientists did some experiment. Let us go for that experiments. But before going to experiment, then what is magnetic flux? We have to know about the magnetic flux, right? Now, the magnetic flux is that. What is magnetic flux? Magnetic flux, right? We have to change the magnetic flux, then only current produces. Then we have to know about the magnetic flux. The magnetic flux denoted with phi suffix b also, phi suffix b, or simply phi also. Then what is the magnetic flux? This definition is the number of magnetic lines of forces passing normally through a given area is called as magnetic flux. That definition is the number of magnetic field lines passes normally through a given area is called as magnetic flux. This is the magnetic flux. What is magnetic flux? How many lines passing normally through a given area? That is called as magnetic flux. Let us see with example the magnetic flux. The number of magnetic field lines passes normally through a given area. For example, this is a paper, we are placing it here. Okay, this is a paper, this is a paper. And here this paper we are placing in the magnetic field. We are placing in the magnetic field. And we are taking the small area. How to place this paper in the magnetic field? We have to place one north pole at here. And here we have to place one south pole. Then the field will be now north to south. In between here one paper we are placing. Then here the paper is like this there. The area vector is always perpendicular to surface. Right? Here I am taking the small area dA. Then the angle between the area vector and field is considered as theta. Then magnetic flux through the small area we can write. How to write? What is the formula for that? Okay, right. Now for that, let us see magnetic flux. Magnetic flux means how many lines passes through certain area. Magnetic flux through the area d suffix dA. That is a small magnetic flux we write to small area. We write as B bar dot dA bar. If you want the total magnetic flux, we write the formula like this. The total magnetic flux is, that is, we have to do the integration. That is integration B bar dot dA bar. Integration gives the total magnetic flux. This is the formula for the total magnetic flux. But here sometimes if field is constant in uniform magnetic field, okay, we write BA is constant, we write outside, integration dA is A, then this we will write as B constant means we write B integration B bar dot dA bar. Okay, and that is nothing but we will get if uniform magnetic field, this B we write outside, the magnetic flux formula will become B bar dot A bar. This we can also write as BA cos theta. This is in uniform magnetic field. There are two formulas are there. This is for variable B. This is for constant B. Okay. Right, if B is constant in uniform magnetic field, the above formula will be like changes like this. This is the two formulas for the magnetic flux. Okay, this is for the variable field, this is for constant field. Okay, this is for variable field, this is for constant field. What are the terms which are present in this? Okay, you take the screenshot and I will continue. Okay, but after the rubbing. Okay, you see here, what are the terms here? B is the magnetic induction. Magnetic induction. Okay, its unit is Tesla. And A is the area, surface area. Okay, theta is angle between B bar and A bar. Okay. A bar is always perpendicular. A bar is the area vector. Area vector is always perpendicular to surface. We know already, right? And now the flux may be positive or negative. Okay, it may be anything. Just one example I will give to calculate the flux. Okay, right. Let us go for that example. And for that, see here one example to calculate the magnetic flux. Just here, this is one cylinder. We are placing this cylinder in the external magnetic field. This is the magnetic field. This is the magnetic field. Okay, right. Now the cylinder is placed in the magnetic field. It has three surfaces. The first surface is S1, the second surface is S2, the third surface is the curved surface, that is S3. Okay, I want the magnetic flux through each surface I want, and the magnetic flux link with the cylinder I want. What is the magnetic flux link with the cylinder? What is the magnetic flux link with the cylinder? This is my question. Right. Now for that, first we have to calculate the magnetic flux link with the magnetic flux through the S1. We can write flux through the S1. Okay, flux through this surface. Here the field is right side. The field is right side. And the area vector for this surface, actually remember that the area vector is always perpendicular to surface. How the area vector will be there? For example, this is a object. For this surface, area vector is perpendicular to surface. For this surface, area vector is perpendicular to surface. That means if you have the cylinder, for this, for the left end, the area vector is left side. Like this, it will be there. This is the direction of the area vector. And this the field is right side. Applied field is right side. Already they gave in the diagram. Then the angle is 180 degree, right? Here for the second surface, the field is right side, and the area vector perpendicular to surface. Area vector is also right side. Okay. Then the angle is 0 between the B bar and A bar for the S2 surface. What about the S3 surface? You take small part on the S3 surface, right? And area vector is like this there, perpendicular to surface, S3 bar, but the field is right side. Area vector is right side, S3 bar. Okay, and area vector here is, area vector is above, will be there. This is the area vector, but the field is right side. They are perpendicular to each other, right? Then flux through S1, flux through S1, what happens is phi 1 we take, that is a B bar dot A bar, and B A cos theta, theta is 180. Okay, right, and then cos 180 value is -1, minus BA we write. And the flux through S2 we want. Flux through S2, that is phi 2, that is a B bar dot A bar, BA cos theta. Theta is 0 at here because B bar A bar parallel. We write cos 0 value is 1 plus BA we will get. And flux through S3 I want, flux through curved surface. S3. Then we write phi 3 is equal to B bar dot A bar, BA cos theta, but theta is 90. Cos 90 value is 0. Then the total flux I want. Total flux through the cylinder. What is the total flux? We have to add all the fluxes. There is a phi 1 plus phi 2 plus phi 3. Then here we will get as minus BA plus BA plus 0. Then finally we will get the total flux as 0. That means the total magnetic flux is 0 in this example. Okay, right. And let us see one more point related to this. What are the units of the magnetic flux? SI unit of magnetic flux or the unit of magnetic flux, let us see. The unit of magnetic flux. SI unit is Weber, that is WB. CGS unit is Tesla. CGS unit is Maxwell. Okay, right. And what is the relation between the Weber and Maxwell? 1 Weber is equal to 10 power 8 Maxwells. 1 Weber is equal to 10 to the power of 8 Maxwell. But according to formula also we can give the unit, that is the flux is equal to B into A, that B is the Tesla BA, flux formula BA, A is meter square, Tesla meter square is also unit. Okay, right. This is about magnetic flux. Magnetic flux is the formula is, in case of variable magnetic field, we have to use, if B is variable, okay, we have to use the integration method, that is integration B bar dot dA bar, or otherwise integration B bar dot ds bar. And in case of uniform magnetic field, we write directly magnetic flux as B bar dot A bar, that is BA cos theta. Okay. Now take the screenshot and let us continue.